Can you imagine 500 million plastic bags are used worldwide? More than 1 million plastic bags are used every single minute. And you know how bad it means? Over 1 million turtles, whales, seabirds, you name it, are killed by marine plastic pollution annually.
This is the Pacific garbage patch. 99% of those are plastics. Nearly every group has emphasized and highlighted the seriousness of microplastic pollution. Plastic cannot decompose. They degrade into toxic microplastics, which are generally less than 5 millimeters in diameter. Plenty of fish regard these tiny plastics as their food. Following the food chain, you will be the next eating the microplastic in seafood. Is that what you want?
That's enough. The era of plastic is over. To save our ocean, we are more than glad to show you our remover scheme. Basically, our device here detects microplastic with sensors and collects them. After that, we'll show you how to recover those collected microplastic.
Sustainability is what the global community looks for. When we take our lunch break, we realize that Ocean Power also incorporates solar power for electricity supply. That's exactly why we use a rechargeable lithium-ion battery in our devices. It can be recharged for over 1,200 times, which is pretty environmentally friendly. Moreover, weather conditions have little effects on our device. When it's sunny, the solar panel will charge the battery. When it's cloudy, the battery can power our device using the stored energy.
Solar power genuinely saves money and the limited fossil fuels we have.
True. Solar batteries enable our propeller to rotate. The propellers are thin, have suitable surface area to provide a thrust force, but at the same time avoiding excess water resistance, so that it can allow a smooth journey along. Let's see how it operates. As we see here, when the switch is turned on, the blades will start to rotate, and this can create a thrust force and allow the remover to move in the sea. And the device patrols around regions with high concentration of microplastics. When the sensor detects microplastics, the door will open and allow their way in. In our model, the light sensors are used. My partner will now demonstrate. When her finger, which resembles the microplastic, arrives closer to the sensor, the door moves upwards and allows the microplastics to enter. And the logic, it's easy to follow, but the theory may not.
A research shows Raman spectroscopy could be used to identify microplastic, and we propose to use this idea to the ocean. Now let's make it simple. Different microplastic molecules have different size and different structures with different chemical bonds. When light radiates to those microplastic, they vibrate in different patterns. As you see for PC, it vibrates more frequently. And for PVC, which is lower than PC, it vibrates less frequently. And a lot of these vibrational values have been collected in the so-called polymer library. What we can do is to insert those range of each microplastic in our sensor. So when microplastic is present, our sensor would be the first to know.
That's right. They are sensitive to the smallest molecular difference in bondings. Plus, water does not interfere with the spectral analysis, which suits perfectly in our device. The process of detection is quite complex. Let's move on to something simpler, collection.
Now, the microplastic would basically pass over the filter. which is about 1 micrometer in diameter in the actual model. It helps remove other larger particles. Besides, the high density of our net will also help collection more smoothly. Finally, they arrive at our collection bag.
When the collection bag is full, another sensor would be notified. It will retreat to our station by the coastline. The bag would be removed and replaced by a new one.
It's not enough just to collect the microbeads. We have to separate them and reuse them. Here's the last part of our plan.
What are these values? They are the softening points of different plastics. As different plastics has different softening points, it is vital to separate them before the final stage, recover. We are going to separate them according to their densities. When they're mixed with salt solutions like sodium chloride and zinc chloride solutions, the denser plastic sinks while the lighter one flows on top. If we are given microplastics derived from a typical plastic bag and a water bottle, you will be able to tell them apart.
After separation, different types of plastic would be given out. Part of them will be given to the medical industry to make syringes and artificial limbs, while some polypropylene could be given to factories to make some plastic products you use every day, like the chairs you're sitting, the water bottle you use, and many more other plastic objects that you need in daily life.
Are you using plastic to recreate more unwanted plastic? I've got a better idea. In 2018, scientists accidentally made a bacterial enzyme, which breaks part of a structure of PET. They only need 3 days to digest the plastic bottle, without waiting millions years for them to completely decompose. These recovered plastic could be given to scientists directly for experiments.
I guess that's all for our secret weapon to cure the ocean. Before you forget, I'll give you a recap of our plan. Detect microplastic, collect microplastic, and recover the microplastic for various uses. But at the end of the day, we cannot save the ocean without your help to reduce plastic consumption. Let's stand as one for our planet Earth. Thank you very much.
Thank you very much. So now it's the Q&A session for the judges. Judges, please.
Hello. Congratulations. This is a very good project. And I have one question, which is basically, one, did you actually test your machine?
We didn't put it into the water to test as it is a prototype, and the water resistance, maybe some of the electric circuit are not water resistant at this point. So we just want to test out different parts of our device, like whether the sensor works and whether the solar panel can really charge the battery.
My second question is, what kind of sensor are you using?
And now we're using light sensor to replace the Raman spectroscopy sensor.
Okay, because how will it distinguish plastic from other type of waste? Or even fish or anything else that you would find in the ocean?
Raman spectroscopy, their sensors are actually specific to the vibrational frequency of each small molecular items. So we firmly believe that this can tell the fish and other waste you mentioned apart, because...
Right. But if you look at the ocean, it's all together. You have planktons, you have microplastics, you have everything in the same place. So...
Yes, so initially we actually put our device to a region which has high concentration of microplastic. That's the setting of our device.
Thank you. Thank you so much.
Thank you very much.
Thank you very much. Very powerful presentation and innovative idea. Have you thought about what are some of the potential, I guess, animals that could enter your device, or would it be possible that it's eaten by marine creatures who mistaking it as food?
I think that some microorganisms, or as the judge said, the plankton may enter it, but
we don't care about them, right? Just kidding. It's okay.
Of course, we care about them. So this is actually a prototype, but when you mention about marine animals, we also think about their safety. So maybe we can try to vary the current emitted by our device. So when the animals think it is not safe to enter a region with like high current or high vibrational frequency, they would probably turn it away. And this prevents them from thinking it as their food. That's what we sincerely hope.
Okay. Thank you very much.
Hi, ladies. Thank you for your presentation. So I understand this is a prototype, but there are a couple of things that would need to be done to make this a workable unit. Can you list some of those things that you would do and that would take into consideration?
as the Raman spectroscopy sensor, it's still used in a large machine in the laboratory nowadays. So it cannot be used outdoors or in a very small scale recently. So we may want to test how to convert or use similar theories used in the Raman spectroscopy and use it into making a smaller sensor that can fit into our device and at the same time can distinguish the microplastics and other things apart.
Is that it?
Apart from that, we've mentioned that the microplastic collector will enter this net bag, but we think that the net bag might not be as strong when it comes to the actual marine community. So we will replace this bag with a bag which has higher tensile strength, and it will not be attached like this. It will be actually attached by magnet, so it will be removed smoothly and enhance the effectiveness of this process. So yeah, these are a few things that we take into consideration.
Mm-hmm. I think you forgot one that you mentioned already. It needs to be watertight, right? So you need a better vessel.
Yep.
Also, I heard you say that the bag, you would remove the bag. So have you given some thought to how you would get the device back to you? How would you maybe code it to have a certain pattern as it would, work through the water? Have you thought out what kind of, in a sense for me, it would be a flight plan. In this case, it would be your water plan.
We actually want this boat to go back to a port or like a station somewhere by the coastline, by different regions of the coastline. So it can go to the station which is closest to our station and remove this bag and replace it with a new one. So yeah, we'll try to a station.
But every time we remove the plastic bag and replace by a new one, it may be a problem in the sustainability. So we will also work on, as my partner just said, will increase the tensile strength and also maybe the density of holes. Although the hole size may be smaller, but the density will be large enough to allow the water to flow out of the device so that it can have efficient and effective collection of microplastics.
Okay, thank you.
Thank you very much.